What factors affect rate of a given reaction? To know this in detail, it is better to look into collision theory. Collision theory basically has certain postulates that you have to remember, might come as a statement question for you. Basically, what the theory deals with is collisions between reactant molecules. So, what is the number one criteria that you can see for our reactants to give you products? The molecules have to collide with each other, obviously. So, a collision must happen. But just because a collision happens doesn't mean that it is going to be effective. For example, let's take our simple organic reaction. RCl plus H2O gives you ROH plus. So, I have replaced this. So, I have to get my HC. Alright, this is what I have. What if my R molecules and C molecules, so just imaginary, they are present in this orientation and our water molecules are present in this orientation, ignoring the shape. Okay. If this comes and collide with this, it's not going to be useful. The first step has to be this lone pair has to come and hit the R. So, couple of things that you want to know: how frequently the collisions happen. Okay, that is called frequency factor. How can you increase the frequency factor? By taking more of the reactants. For example, imagine that the room that you are sitting in right now, if there is a lot more people, the frequency of the collision is going to be high. Just because the frequency is high doesn't mean the reaction will go much faster. The collision has to be effective. What is meant by effective? There are two things that you want to know. One is the orientation of the molecule. This orientation is not good. The orientation is better if it is this way. So, this is a better orientation, this is not a good orientation. So, orientation of the molecule is going to contribute to effective collisions. Effective collisions are the ones where, let's say there is 100 collisions that happens in your room, maybe 30 of them will give you products. That 30 is called an effective collision, the remaining 70 are called ineffective collision. The effective collision has to be the right orientation, and also they have to have the right energy.
The first assumption of the collision theory is that the particles must collide with one another in order for them to react. In most cases, when the molecules collide, they behave like billiard balls or carom board coins. They meet each other and most of the time they go away. Now, collision isn't all that is needed for the reaction to happen. The molecules need to have enough energy to break and form new bonds. The amount of energy that they have to gain is called the activation energy. For some reaction, the activation energy is larger, and for some reaction, the activation energy is smaller depending on the type of bonds broken and formed. Generally speaking, when you increase the temperature, the activation energy is easily attained, so the rate of the reaction is much faster. That's because you are increasing the kinetic energy of the molecules, thereby increasing the frequency of collisions. But temperature isn't the only factor, the orientation also matters. It's like meeting the right person at the right time. If the orientation of the molecules are not aligned well, for example in our case here, nitrogen monoxide and ozone, the oxygen and oxygen collided, giving rise to no fruitful collision. Whereas now when you see the orientation is perfect, that the nitrogen and oxygen meets and ozone gets converted to oxygen and NO becomes NO2. Now in summary, we can see collision theory has three postulates to it. The particles must collide and the collision should have sufficient energy and correct orientation must be present for the collision to be fruitful. Let's briefly look into the thermodynamic aspect of the collisions. We saw the right orientations and also about the activation energy. Now let's look at specifically at the temperature. The temperature, as we just said, is the average kinetic energy the molecule possesses. We can increase the kinetic energy by increasing the temperature, and what happens when we increase the temperature is the number of molecules possessing the higher kinetic energy keeps increasing. We can actually look at it in terms of a plot.
This can be our fraction of molecules that have a certain amount of energy. This is the kinetic energy of the given molecules, reactants. So, how is it distributed is somewhere like here. This is how it is distributed, meaning the fraction of molecules with this kinetic energy is only so much, whereas the fraction of molecule with this kinetic is so much, this is so much, this is so much, so on and so forth. From our equilibrium, And thermodynamics, we know this graph. This is the activation energy. So what is this total energy called? We have seen that this is our threshold energy. So collision is effective when it has the right orientation and also the molecules have enough energy to cross the threshold barrier, okay, or basically an activation energy barrier. So you need to gain certain amount of energy. So how much of these molecules cross that activation energy barrier? You can say, for example, somewhere here, E activation. So there are molecules, but most of them don't cross the activation energy barrier. When I increase the temperature, the graph changes into something like this. What we have done is basically flatten the curve. So now, this used to be the fraction of molecules that had required amount of energy above the activation energy, whereas now by increasing the temperature, I have flattened the curve, the fraction of molecules has increased considerably. So increasing the temperature increases fraction of molecules going to the product side regardless of whether this is endo or exo. It doesn't really matter. By increasing the temperature, you have made more of them go. So this is the basic importance that you want to know. By increasing the temperature, the fraction of the molecules that possess the threshold energy increases. So if I can increase my orientation and I can increase my fraction of molecules. The orientation is very simple. For example, if I were to replace this SN2 reaction, it is important that the nucleophile comes and hits the central atom. What if it is going to be this way? It's not going to be effective. A nucleophile and nucleophile meeting is not going to be effective. So it has to be the right orientation and the right energy. So this is going to affect your rate of reaction. Now we have seen about orientation and also the threshold energy. What else can affect rate of a reaction? Now obviously your physical state of a reactants matter. In general, a gas phase reactant can react much better than a liquid phase compared to a solid phase. The next thing that can affect is the size of the particles for a solid state reaction. The smaller the size, the better it is because the surface area is very high. Now this can come only as a statement question. The other thing that we can do is, we know a rate law. Rate equals some rate constant times concentration of the reactant to the power alpha. So now we know the rate is dependent on K and the rate is dependent on R. So you can increase the concentration of the reactants. But if there is a question, increasing concentration of the reactant increases the rate always. Is that true? The answer is no. What if that particular reactant is not in the rate determining step? So it might not be useful. In general, if this R molecule is in rate determining step, then increasing concentration of that is going to increase the rate. Pretty straightforward. Now, how can we increase K? You increase the temperature. K is dependent on temperature. So, if you increase the temperature, K increases, hence rate increases. Now, this has to come to temperature coefficient. Let's look into how temperature affects rate of reaction. We already saw in equilibrium, temperature affects the position of equilibrium. Let's just do a quick refresher. In an equilibrium reaction, for a system at equilibrium, let's say R gives you products. We can have two different conditions, exo or endo. If forward is exo, the reverse is endo, or vice versa. So what happens when I increase the temperature? Exothermic reaction loves to give out heat. So they don't like temperature. They want the surroundings to be colder so they can give the heat out. So by increasing the temperature, I am actually making the exothermic reaction go backwards. So it's a reactant favored. Endothermic reaction wants the heat, so it will take the heat in terms of temperature and it will go forward. So increasing in temperature makes the exothermic reaction go backwards, endothermic reaction go forward. But increasing in temperature changes the rate completely. It actually makes both the reaction, doesn't matter forward or reverse, it makes both the reaction go faster. So this is something that you want to remember. Rate is always proportional to temperature. Does not matter exo or endo. For example, It's an exothermic reaction. It makes that increase in temperature makes it go to the reactants. An equilibrium always is going between reactant and products concurrently. Okay, it is be in a dynamic equilibrium. By increasing the temperature, I have just made this reaction faster. That's all. But it is going to go to product or reactant doesn't really matter. Whatever direction that the equilibrium has decided that it has to go, kinetics is deciding do that faster. That's what temperature does. So you have to know the differences between them. A capital K, small k, altogether different. If we take capital K, this it can go down or go up. If it goes down by increasing in temperature, then it is an exothermic, this is an endothermic reaction. Whereas a smaller case K is directly proportional to T, meaning increasing in temperature always increases the rate constant. How much does it increase? That's called a temperature coefficient. Now what we can do, we can compare the same reaction at two different temperatures, and the best way to do that is do it in a temperature that is 10 degrees apart. So let's say we do a reaction rate. Rate 1 is rate constant times concentration of reactant, and I can do the same reaction this time. I can increase keep the concentration same, increase the temperature, meaning my K is different. I can increase this as T and this is T plus 10. Now what has happened is, by increasing the temperature, I have changed the rate constant, so my rate also changes. Now if I monitor these two rates, I can figure out what happens. Now your temperature coefficient is given by the symbol mu, is nothing but the ratio of specific reaction rate or rate constant at two different temperatures separated by 10 degrees apart. For example, I can do this at 30 degrees, 40 degrees, 75 degrees, 85 degrees, doesn't really matter, but they have to be 10 degrees apart. This is called a temperature coefficient. Most reactions, unless the examiner tells so, the test tells so, most reactions is generally double for every 10 degree rise in temperature. So this is the temperature coefficient. How is this useful in figuring out rate of reaction when you change the temperature by x degrees, not necessarily 10, x degrees. So extremely simple. What we can do is rate, let's say rate 2 by rate 1. Our initial rate after I increase the temperature, final rate is nothing but a temperature coefficient to the power delta T by 10. What it basically tells you is, imagine that you have a reaction and you increase the temperature by 10 degrees. The rate has become doubled. Okay. What if you increase by 20 degrees? You have increased it 2 times 10 degrees, right? So the rate doesn't become times 2. What happens is, it becomes 2 to the power 2. Whatever the rate is, it has doubled, and then the double has become even more double, meaning quadrupled. So hence you have a power not multiplied by. Delta T by 10 tells you how many 10 degree changes you have done. This we can understand actually by looking at an example. In 2012, this has been asked. In a zero order reaction, every 10 degree rise of temperature, the rate is doubled. If the temperature is increased 10 to 100 degrees, what will be the rate of a reaction? A couple of things they have told you in the question is, the temperature coefficient has been given as 2, meaning for every 10 degree rise in temperature, the reaction doubles. So temperature coefficient is 2. Now what will be the final rate? Basically you are going to do mu to the power delta T by 10. Mu to the power delta T is nothing but 100 minus 10. So you went from 10 degrees to 100 degrees divided by 10. So that is going to be mu is 2 because the reaction doubles. They have given you it doubles, so mu is 2 to the power 100 minus 10 is 90 by 10 is 9, 2 to the power 9, which is 512. So the rate, when you raise the temperature from 10 to 100 degrees, the rate at 100 degrees is 512 times faster than the rate at 10 degrees. Now, does this question tell you it's exo or endo? Doesn't really matter. regardless of it is exo or endo, the rate is going to be faster, and that's the unique property of rate compared to your equilibrium. So we have seen many times throughout this lecture that the rate constant is affected by the increase in temperature. Now why does this happen? Imagine increasing in temperature. Temperature by definition is basically a measure of the kinetic energy of given molecules. So by increasing the temperature, you are basically increasing the kinetic energy. The higher the kinetic energy, the more the collision is going to happen. So the more the collision, obviously, the more it's going to be the number of effective collision, hence the number of products formed, hence the rate of the reaction has increased. Now Arrhenius gave an equation relating the rate constant versus the temperature. It's called an Arrhenius equation. Rate constant K equals A e to the power minus EA by RT. Here K stands for rate constant or specific reaction rate. A is the frequency factor, Arrhenius factor or collision factor. E is the activation energy, R is the gas constant, and R has to be in 8.314 joules per mole Kelvin. T is the temperature in Kelvin. Now, obviously this equation we have to take ln on both sides. Ln K equals ln A minus EA by RT. Now we can also convert this to log. It comes to log K equals log A minus EA by 2.303 RT. I have just taken 2.303 out of here and basically divided. We can do at two different temperatures. Let's say at temperature 1, I can have log K1 equals log A minus EA by 2.303 RT1. At temperature 2, log K2 equals log A doesn't change minus EA by 2.303 RT2. By increasing the temperature, you are not going to change the activation energy. You are just going to make it go higher. Now what we can do, how can you compare at two different temperatures? We can do equation at T2 minus T1. So log of K2 minus K1 is log of K2 by K1 equals log A goes away. I'm going to take the minus inside. EA by 2.303 R 1 minus T1 by 1 minus T2, or you can do T2 minus T1 divided by T1 T2, however you want. You want to remember this equation. Questions do come based on this. This is extremely simple, the temperature dependence of rate. How do they give you this? They don't give you K2 and K1. Normally they tell you the rate has become so many times. At temperature 1, the rate is X, the temperature 2, rate is Y. I don't have to give you X and Y. Instead, I can say when I increase the temperature from 10 degrees to 25 degrees, the rate has become 6 times. So basically log of K2 by K1, or K is proportional to rate. So 6 times rate 1 divided by rate 1. Rate 1 cancels. Basically they are telling the ratio, 6 times is the ratio. Log 6 equals EA by 2.303 R is in this value, and they are given you the temperature. So what can you calculate based on that? Your activation energy. Conversely, I can give you the activation energy, give you two different temperatures. I can ask you how many times the rate has changed, or essentially the rate constant has changed. This is one pattern of question they have asked you. The other one that you want to know, the same reaction, you can have the same temperature, the K2 can change when the EA changes, activation energy. For what if I can use a catalyst, the activation energy changes. So the rate automatically changes because of that. So I can do the same here, except instead of temperature, I will have different EA values. Let's go to this equation at two different conditions. Log K1 equals log A minus EA by 2.303 R T. Here I have EA1. I am not changing the temperature, I am just going to change the activation energy at two different conditions. Okay, now we can do one minus the other. I can get the same log k2 by k1. Log k2 by k1 means this minus this equals, so this minus this log a cancels, minus ea2 minus of minus ea1 is ea1 minus ea2 divided by 2.303 RT. Maybe I can just write it down. K2 by K1 equals the change in EA divided by 2.303 RT. So I can ask two different things. I can ask you what is the change in activation energy, or I can give you the activation energy. I can ask you what is the new activation energy. Again, these do come from the same formula. I wouldn't say memorize it. If you just remember this and you can get it, or by practice you're going to get this. So many questions come out of this. Now again, K2 and K1 are rate constant directly proportional to the rate itself. So if the rate has become x times more, meaning K2 by K1 ratio is also x is to 1. So you want to remember that. Then you can do that easily. And I can give you everything on the right side, ask you what is the change in rate as well. Let's have one last problem in our Arrhenius equation. We will go to a NEET previous year questions. In this particular question, if you see, they have given you the rate constants for two different reactions as K1 and K2, and they are asking you at what temperature will they be equal. So they are asking you when is K1 equals K2. So we know in general K equals AE power minus EA by RT. So they are asking you when is K1 equals K2. So K1 is given as 10 to the power 16 e to the power minus 2000 by t, that should be equal to 10 to the power 15 e to the power minus 1000 by t. Now we have to just mathematically solve. Now the chemistry part is pretty much done. We have to mathematically solve it. We can right away say that's 10 power 15 goes away. I have 10. So I have 10 e to the power minus 2000 by t equals e to the power minus 1000 by t. We can take ln on both sides. Ln of AB is ln A plus ln B. Ln of B is actually here minus 2000 by t. So I'm going to get a minus 2000 by t here equals ln of e to the power minus 1000 by t is minus 1000 by t. Just a quick thing, ln is base E, log is base 10. Ln of base E to the power E is 1, 10 to the power 10 is 1. Now that we have it, we just have to simplify it. So that tells you ln of 10 equals, this goes to the other side, 2000 by t minus 1000 by t, that is going to be equal to 1000 by t. Ln of 10 can be written as 2.303 log of 10. Log of 10 is 1. So we can write t equals 1000 by 2.303. Now obviously this is in kelvins because this is always in 8.314 joule per mole Kelvin and temperature is in Kelvin. So hence our answer. Now Arrhenius equation, what all can you change? I can get two different K values, two different temperatures, two different EA, or I can compare two different reactions at same temperature, different K values, assuming that the frequency factor is the same. If they don't tell you, you can assume that it is the same.